In this video, I would like to try one more time to show you how to write a greatest common divisor algorithm inside of C++ that not only finds the GCD of two numbers using the Euclidean algorithm, but also uses the power of the Euclidean algorithm to come up with this quantity for Bezout's identity, which is something we're going to need as we get into some applications later on. So I'm going to remind you what that is. When we find the greatest common divisor of two integers, Bezout's identity says that there is a way to take that greatest common divisor and write it as this so-called integer linear combination of the two values that you started with. So all that means is that we can find integers s and t, for which that GCD can be written as the first number times the integer s plus the second number times the integer t. So the GCD part of this is not horrifically difficult using the Euclidean algorithm. All we have to do is take our two integers, a and b, and we need to look at the quotient, which is the result of doing integer division, and the remainder, which is the result of using the modulus operator. And what we have in this situation is that our a value is equal to the quotient times the b value plus the remainder value. And the Euclidean algorithm tells us that the greatest common divisor of the a and the b in this instance is equal to the greatest common divisor of the b and the r. Furthermore, we know that as soon as we get a remainder of 0, we have a division going on between our a and our b values. And in that case, the b value, which we're assuming to be the smaller value, is going to be that greatest common divisor. And so that sets up the recursion in our function. If we found a place where that remainder value is equal to 0, then we have a division going on. B is the smaller of these two values, and the GCD should just be equal to the b value. If our remainder is not 0, however, that means we need to keep going. We need to call the Euclidean algorithm function again, with the b value now being the larger value, or the a, and the remainder value serving as the new b. And that's it. If I run my program right now, it'll get me the GCD of these two numbers, 3084 and 1424, that I started with. So that part of the Euclidean algorithm is not too difficult. What is difficult is returning more than just this GCD value with each function call in order to do the bookkeeping that's required for Bezout's identity. So let me just show you what I want to do. Instead of passing just the GCD as a return value, what I want to do is create a little struct that I've called a Euclid that contains the GCD, but also contains two integer values that I've called s and t, and they are serving as sort of the s and t at this level of function call. And really what they are going to be are coefficients on the a and the b value at this level of the function call, which are really the b and the r value of the previous function call. And they're going to keep track of how many copies of that a and b value I need in order to get this GCD. And then what we need to do is a little bit of bookkeeping to update the s and the t values at the next level of function call. So let me take a visual to show you how that works. So let's think about that function that we wrote, and everything here is going to be written symbolically. At one level of a function call, the very first thing we do in the function is write a as q times b plus r. We could do that integer division and that modulus operator to get these values. And if I were to rearrange this equation and subtract q times b from both sides, I could think of that as this equation that I want to highlight. A minus q times b is equal to the r value. Now the b and the r value, if we were working sort of top down to get this GCD of a and b, if this r value is not 0, we're going to call the function again with the b serving as the new a and the r serving as the new a and the r serving as the new b. So let's think about what happens when our previous function call returns something. It returns the GCD and it returns these two integers that I've put as part of the Euclid struct, which are an s and a t. This level of the function had an a and a b and an r, and then the a of the previous function is b, and the b of the previous function is r. So this is what is being returned to us from the previous function call. Now, the GCD is being passed up along each function call. The GCD of one level is equal to the GCD of the next level is equal to the GCD of the next level. So the GCD, we're just going to keep that. Whatever the GCD is just gets passed from one function call to the next. But we need to update this s and this t value appropriately. And the way that we're going to do that is to get rid of this r value by substituting this yellow equation in here for this r value, and then doing some arithmetic. So what I've shown in the very next line of arithmetic here is what happens when I symbolically put parentheses around a minus qb and change out the r for that value. The very next thing that I want to do is whenever I have one thing out here in a big set of parentheses mathematically, I want to distribute that t element to both pieces of the parentheses, and I get this three-termed equation right here. However, here I've got a TA, and here I've got something with a b in it, and here I've got something with a b in it. I would like to, in my next step, rearrange this equation so that the two terms that have b's in them are right next to each other. So that's all I've done going from this line to this line. The t and the a are now first, and these two things with b's in them come second and third. But the whole purpose of this rearranging is to get another thing of this form that's in this, let's change it to green now, this green box right here, in order to pass that up to the function that called us. So what we want to do is have GCD is equal to what's going to be our b value here and our r value here. Gotten rid of this r, so I want the a and then I want the b. So all I have to do is condense this b over here, factor this b out of both terms, and put it over here. So this b is serving as the new r, this a as serving as the new b, and what's left in parentheses here is going to be this new coefficient. So from the combination of these two equations, I've now gotten something that matches, something right here that matches what I had up here. GCD is equal to some coefficient times a plus some coefficient times b. And what our new coefficient on the first term is just exactly what this coefficient was right here. So this t has just moved over to be the coefficient here. The new coefficient on the inside is a combination of these other things. Whatever this s value was, I want to take it and I want to subtract q multiplied by this t value, and that becomes my new coefficient here. So that's all we need to add to our program. If I return to my Visual Studio document and I come down here, let's set my ret values s value to just be equal to my previous ret values t value. And the ret value in the spot of t was more complicated. That was my previous ret values s minus the thing I'm calling q times the previous ret values t. And those are the new values that I want to pass on to the function before me. And now, if I come back up to main, I can write my common divisor GCD is equal to, and we can double check that this is actually the right value. And if we go ahead and run that, we see that we have this decomposition, and when C++ does the computation, it actually gets the right answer, so we're done.